Okay, so today's lesson is Unit 1 Kinematics, Lesson 4 Motion Graphs. So we have done a lot of motion graphs. We've looked at position time graph, velocity time graphs. Today we're going to add acceleration time graphs and sort of combine them all together. So we did look before at velocity and position time graph, where we learned that if you can find the slope from a position time graph, you can get the velocity. And if you find the area from a velocity time graph, you can get displacement. Not directly position, but displacement. Similar rules apply between velocity and acceleration. If you can find the slope of a velocity time graph, you can get acceleration. And if you can find area under an acceleration time graph, you can get change in velocity. Okay, similar to how we find the area from a velocity time graph, we get displacement, which is change in position. Here, if you find the area under an AT graph, you get change in velocity. We just don't have a special word for change in velocity like we do for change in position, being displacement. Okay, so we're going to analyze some examples so that we can get better at these. Here's our first example. First example says to analyze this dt graph. So this is a position time graph. It says at what time is the velocity 0? So to find velocity, you need to find the slope. And if the slope is horizontal, meaning the slope is 0, velocity is 0. And that'll happen at a couple places. Here, at this peak, you will have kind of a slope like that. At this peak, you'll have a horizontal slope like that. And up here, you'll have a horizontal slope like that. Okay, so you have 3 times where it's going to happen. Looks like we can sort of estimate right here, maybe at 9 seconds. Here at 13 seconds. And here at what looks to be about 18 seconds. So that's when your velocity is going to be 0. Next it says, what is the average velocity from 5 to 15 seconds? So to find average velocity, we're going to connect the points. So here's 5 seconds. And 15 seconds is right there. So I drew a secant between those 2 points. And what we're going to do is to find the velocity, we need to find the slope. So let's look at the slope. It's rise over run. Here's our run, and here is our rise. So our average velocity. We rise over run. Now rise, we go from what looks like about 7 meters, and here 4 meters. So 7 meters minus 4 meters. Over our run, which is between 5 and 15 seconds. So 15 seconds minus 5 seconds. So on the numerator, we got 3 meters over, forgot the seconds here, over 10 seconds. Okay, so you get an average velocity of 0.3 meters per second. So in part C, it says, what is the instantaneous velocity at 15 seconds? So I want to know the velocity right there at 15 seconds. To do that, I have to draw a tangent to that point. So again, in grade 11 physics, we are going to sort of estimate a tangent. It'll be something like this. And then what we're going to do is we're going to pick 2 points on that tangent so we can find the slope. I'm going to try to pick nice points. Like perhaps this is right at 2, so I'll pick a point there. And maybe this one right at 8, right there. So we'll get our rise over run. Like that. And now we're going to calculate your instantaneous velocity. So our rise seems to go from 8 to 2. That's how I chose it. So 8 meters minus 2 meters. And our run seems to go from, let's see, 10, 11, 12, maybe about 13 and 16. So 16 seconds minus 13 seconds. So 8 minus 2 is 6 meters over 16 minus 13, which is 3 seconds. And that gives you 2 meters per second. So that would be our instantaneous velocity at that point. And different students might choose slightly different slopes based on how you draw your tangent, but you should not be getting things like 0.1 meters per second or 5 meters per second. You might get 2.2 or 1.8, right? But the slope shouldn't be too different. So in the second example, we are given a velocity time graph, and we have to draw both an acceleration time graph and a position time graph from this. So let's first look at the velocity time graph, see what's actually happening. Let's say it's a car. Right, so we have a car initially moving at minus 10 meters per second east, which is the same as 10 meters per second west. But then the car is slowing down, eventually reaches 0, and then starts moving east instead as it speeds up. And as it speeds up, it then reaches a point here where immediately it changes direction, and not changes direction, but starts to slow down. It's still heading east until we get to this 0 point. And now its velocity starts heading west again. So now we change direction until it reaches a constant velocity and continues at that constant velocity for the remainder of the time. Now, if we want to draw a position time graph, what we have to do is figure out the area under the graph. So we have a couple different places. Let me just draw a line right across here. So that's our origin. So we're going to look at the area right here first. So to calculate that area, I'm just going to do it on the side. We'll call it A1. It's a triangle. So that's just 1/2 base times height. Our base looks to be 2 seconds, and our height minus 10 meters per second east. So 1/2 times 2 seconds. I'm going to run out of space. Let me just move over a bit. Times minus 10 meters per second east. Okay, so 10 times 2 is 20, divided by 2 is 10 again. So we get an area of minus 10 meters east. That's our displacement. So during that first 2 seconds, we've moved 10 meters towards the west. Negative east would be west. So we've moved 10 meters negative east. Now, nowhere in this velocity time graph does it tell us where we're starting from. So I'm just going to assume we're starting at the origin. So here's our starting point. And after 2 seconds, we've gone to a position of minus 10. So we're right here. So we have 2 dots. Now the question is, how do I connect the dots? Do I connect them in a straight line or some sort of curve? And what we're going to do is use a curve. Now why do we use a curve? Because a straight line in a position time graph would mean constant velocity. And our velocity is not constant. It's changing. In fact, it's slowing down. So we're going to have to draw a curve. Now I can draw 2 different types of curves. I can draw one that looks like this, or I can draw one that looks like this. So this one or this one. Number 1 does show, if we were to draw like multiple tangents along number 1, you can see the slope of the tangent decreasing So number 1 shows that we're slowing down. Whereas number 2, if I were to draw tangents, you can see the slope is increasing. So number 2 shows that we are actually speeding up, which is not the case. So we are going to draw the first one. So let me just clear this so I can just draw the first one on its own, like so. Okay. What we're going to do now is try find this area in here between 2 seconds and 4 seconds. Let's call this area 2. Now, if you analyze the triangle, it has a height of 10 and a base of 2. So the value is going to be the exact same we got for A1, except that it's positive. So it's towards the east. So A2 is going to be positive 10 meters east. So now we're moving 10 meters to the east. So this is our initial position here. And we're going to move up 10 meters. So we're back at the origin at this point. Now over here, what we're doing is our speed is increasing. So another question again, if our speed is increasing, we should draw a curve. Should that curve look like this, or should the curve look like that? Right? So we're just going to draw the curve here that shows an increasing slope like that. And we're going to continue this pattern. So this is A3, which is also, if you look at the area, going to be 10 meters east. So we go another 10 meters east. But in this case, we're slowing down. So we're going to draw a curve that shows a slope that is slowing down. And then over here, if we call this A4, A4 is similar. And it has an area of 10 meters. But again, in this case, it's going to be west or negative east. So we had another 10 meters in this direction. And we are speeding up. So curve like that. Finally, in this last portion, let's call this A5. This is just a rectangle. So A5 is going to be length times width, which is 2 times minus 10, which would give us 2 times minus 10 meters per second east. Forgot my units on the 2. Minus 20 meters east. So 20 meters west. So we're going to go 20 meters west, which is going to take us right down off of here, somewhere there. And in this case, we have a constant velocity. So a constant velocity is a straight line on a dt graph, like that. Before we do the acceleration time graph, I think we should take a look at different ways we can draw a position time graph and what they mean. So let me just do a little chart over here on the side. So if we have a dt graph and a vt graph. So on a dt graph, if we have a horizontal line, right, say at 2, a position of 2, well, your position is not changing, so your velocity would also be a horizontal line, but it would be at 0. If you were to have something like this, an increasing slope, then you would have a horizontal line for vt at some positive value. And if you were to have a decreasing slope, then you would have, again, a horizontal line on your vt graph at some negative value. And then we have the possibility of curves. So we have different curves. We have this curve. Now this curve, if you look at your tangents, right, let me draw some tangents. If I drew a tangent at this point, or if I drew a tangent at that point, you can see that that was a terrible line. Let me see if I can fix that. You can see the slope of the tangent is decreasing. And so if the slope of the tangent is decreasing, then on our vt graph, we must show a velocity that is slowing down. And you can do that in two cases. Let me just draw a little coordinate. One, if you're moving in the positive direction, you could do this. So that's slowing down. But another example is if you're moving in the negative direction, you can do this. That would also be slowing down. Do I have more room? I have a little more room. Okay. Other types of curves is I can show a curve that looks like this. Okay. And in this case, if we look at any points there and look at their tangent, like if I looked at this point and then this point, you can see the slopes are increasing. Again, that's a terrible line, but you get the point. Right? Here you have a low slope and then a high slope. So if we were to draw this on our VT graph for an increasing slope, the velocity must be increasing. And it all depends on what direction you're moving in. Right? If you're moving in the positive direction, you're increasing like that. But if you're moving in the negative direction, you would be increasing like that. Let me change my color. So here we have a positive slope that's increasing, which sort of shows this one. But if we were to show what an increasing slope looks like in the negative direction, we can do this. Okay, so that would be the case of an increasing slope in a negative direction, because if you looked at, say, this point or this point, you can see the slope is becoming more and more negative compared to here and here. Okay, and similarly with this one, here we have a decreasing positive slope, which shows right here. I forgot to change my color. It's all right. Whereas here we have a decreasing negative slope, where we can show something like this. So if we look at that one and at any points on that one, here you have a large negative slope, and here you have a negative slope that's not so large. So moving on, if we go and look now at acceleration, the slope on a velocity time graph tells you the acceleration. So we don't need to find the slope in 5 different locations, because this from 0 to 4 seconds is one slope. So let's analyze that slope. So here's our rise, and here's our run. We'll call this slope 1. So acceleration 1 is the slope of 1. Our rise is 10 meters per second. So final minus initial. So 10 minus negative 10. Okay, so we have a double negative there. And that's all divided by our run, which is 4 minus 0. So 10 plus 10 is 20. Divided by 4, we get an acceleration of 5 meters per second squared. Notice that it's positive, because that's telling us then the direction is east. Okay, and it's constant too. So we just write a horizontal line at 5 for the first 4 seconds. And you can do the same thing with this slope. You'll find the same value, except you'll find it to be negative 5 meters per second, or 5 meters per second west. And we can do a line right here for the next 4 seconds. And then, of course, this last portion is just a horizontal line, so the slope is 0 for the last 2 seconds. And that's going to be a discontinuous. Again, in the real world, it would be continuous, but we're not going to look at change in acceleration in this course.